Okay, so we just learned that material that makes Earth, the chemical material that makes Earth, was formed before the Earth was formed. It existed already. And it was actually formed during the Big Bang. The Big Bang was the beginning of our universe. Right? All of the current and past matter in the entire universe came into existence at the exact same time. A moment in time, all of the material came into existence about 13.7 billion years ago. This is the Big Bang theory. Okay? And at this time, all matter was compacted into a very small ball with infinite density and intense heat. Okay? So the Big Bang theory, in the Big Bang theory, we think that a fraction of a second after the Big Bang, a fraction of a second after all of the material in the world was created, formed at this single location, kind of, there was a rapid expansion, right? A fraction of a second after this Big Bang, there was a rapid expansion during a billionth of a billionth of a billionth of a billionth of a second. And the entire visible universe was about the size of a grapefruit. Right? The universe was so small and so dense and so hot, it consisted entirely of energy. And there was no solid material to touch, right? There was no water yet. There was no carbon yet. It was just energy. And then about 100 to 1,000 seconds after the Big Bang, the universe continued to expand, right? Larger than grapefruit. And as it expanded, its temperature dropped to the point that the nuclei of some of the smaller elements could form, right? The elements that just have a few protons and neutrons and electrons, like hydrogen, helium, lithium, those small elements, those could start to form. Then minutes to a couple 100 million years after the Big Bang, and I know a couple 100 million years sounds like a lot, but in geologic time, it's actually very, very little. Right? Minutes to a couple 100 million years after the Big Bang. Again, the universe is still expanding. As it expands, it continues to cool. And the atoms and the molecules start to slow down, right? And they start to accumulate in these patchy clouds that we call nebula or nebulae. Okay. The earliest nebulae consisted almost entirely of hydrogen and helium gas, the lightest elements, right? Those are the elements that were created first, right? They're the lightest, they were the easiest to be formed, they were created first, so they were the most common, and that's why these earliest nebulae were created almost entirely of these light elements like hydrogen and helium, right? Still no water, still no carbon, just those light elements. Continuing on a few 100 million years after the Big Bang, right? In these nebulae, the matter continues to clump together under its own gravity. Every particle has its own gravity. It's going to start attracting other material to it. And as that gravity starts clumping more and more and more material together, we start to see the first proto-galaxies, right? You can think of these as the baby galaxies. And within these baby galaxies, we get the very first stars. Okay, so up until this point, the universe was dark, right? Now we're starting to get the very first pinpoints of light, those first stars. And stars, I think of them as nuclear furnaces, right? There are these furnaces in which heavier elements like carbon, oxygen, silicon, and iron are formed. Remember, in the first nebulae, we just really had those lighter elements, right? The small elements. It wasn't until stars were formed that they could start cooking in their furnaces and create heavier elements. And what I mean by this, what I mean by cooking, in massive stars, lighter elements are actually burned to form heavier elements through, right, bringing this word back up, nuclear fusion. So nuclear burning proceeds until all of the helium and heavier elements are used up. Eventually when iron is formed. All right, so first the smaller elements like hydrogen and helium are burned and used up, and they are fused into helium and neon, and then those are used up and burned into heavier and heavier and heavier elements until we get to the heaviest element that stars can create through nuclear fusion, which is iron. And iron's really unique. It's very stable, right? And because it's so stable, it actually requires more energy to fuse it than it would to just leave it alone. And so iron doesn't burn or it doesn't undergo nuclear fusion within stars. And this process stops at iron. But you might be saying to yourself, well, if it stops at iron, how do we get the elements that are even larger than iron? And this happens when massive stars explode. Okay, so within stars, we can go from very small elements through nuclear fusion as those small elements fuse together to make larger and larger and larger and larger elements until it gets to iron. But to make anything larger than iron, the star actually has to explode. And when massive stars explode, we call those supernovas. Supernovas are these huge explosions of stars that send material into outer space. And in doing so, through this intense release of heat and energy, create larger elements. And those larger elements and everything else that was projected out from this star is then ready to be incorporated into future generations of stars and planets. Right? So you might have heard the famous Neil deGrasse Tyson quote that we are all stardust. Right? Every single one of us, you, me, everything around us, we're all made of stardust. And that's literally true, right? Every single element that we are made of was produced within a star, either through nuclear fusion or through the star exploding as a supernova, right? But we are literally made of stardust. Okay, so we've talked about stars, we've talked about the creation of larger elements. Now we're going to focus in on our specific galaxy, right? And our specific solar system. 9 billion years after the Big Bang, the sun, meaning our sun, our own star. The sun is just a star, but it's our star. The sun, along with its 8 planets and all of the asteroids and comets and other things, formed from the debris left behind by earlier generations of stars. Right? As older stars formed, grew, aged, eventually exploded, projecting their material into space, that material over time was under its own gravity clumped together to form our own solar system.